Well, today we shall continue with our discussion that we carried out in our last class, that is the uniform flow in mobile boundary channel. And we will be concentrating today on the topic that incipient motion condition that we left in the last class, and then from there we will start, and then how once this incipient motion condition is reached and the sediment starts moving from the bed, then how it lead to different regimes of flow. So, that we will be discussing. Just to recapitulate what we did in the last class, that we have seen that to derive the equation of incipient motion condition, there are different approaches. One approaches talk about a computant velocity, then other approaches talk about a force, critical force. Again, this critical force concept that we can again divide it into two parts, or we can just see as a two part. One is where we considered that lift force, another where we talk about the drag force. And in hydraulic engineering, particularly in open channel flow, hydraulic engineers has found that the drag force approach is more logical, because the flow is moving on a surface and the bed material that is over which this forces is exerted is on a bed, and then this surface is basically subjected to the force. So, drag force is more significant, and that way drag force approach is followed, and that way we get a term that is referred as tractive force. So, this tractive force, when it is just sufficient to drag the particle, that is called critical tractive force. And Sealed, the scientist who conducted lot of experiment and observed data, and then he gave some theoretical understanding of the entire process, and based on this theoretical understanding he used some observed data, and then he derived some relationship. So, that we can call as a semi-theoretical analysis, and let us start from that particular point. Okay. Well, incipient motion condition, suppose this is the bed, and let me just draw the particle little bigger, okay, means just to have, say, that way the particles are there, and diameter of the particle is, say, d, diameter of the particle is d. So, we can write this as d. And then when we talk about the drag force, the flow is like that, flow is moving like that. And when we talk about drag force, then basically we talk about a force at this level on the particle. And suppose the flow velocity at this level we can write as u, and as it is at depth d, so we can write it as u d, that is the velocity just at the surface of the particle. Well, now these particles are, when we are talking about erosion by the fluid, that means these particles are always underwater. So, we are interested to know the force required to move this particle, and then we first need to see that what force will be required and to which this force will be proportional. So, if we write that force required to move the particle, force required to move the particles, this force is, rather than going for a definite value first, let me write this force is always proportional to the weight, and then when we say weight, we will have to write the submerged weight, because this will be always submerged. So, we can write is proportional to the submerged weight of the particle. Now, starting with that, what will be the submerged weight, that we can write that F1 Now we can introduce a proportionality constant, say A1. Let it be there, this be the proportionality constant, and then weight will be proportional to the volume of the particle, and the volume of the particles will be proportional to the diameter cube. So, we can write that it is proportional to the diameter cube of the particle, and then as we are already using a proportionality constant A. So, we can just keep it as proportional to the volume, then we write that it is rho, it is the mass. So, we can write okay, this rho means it is what we can write that this is the submerged weight we are talking about. So, we will have to write rho s minus rho, rho s minus rho, and what this rho is, basically we are writing here submerged density, and then we are multiplying this by the g, that is g into rho s minus rho. This is giving us the submerged unit weight, where rho s is the density of the particle, rho s is the density of the particle, sediment particle, and then rho is the density of the fluid, density of the fluid, here it is water. So, when we multiply it by g, we are getting unit weight, and that rho s minus rho, that is why we are getting submerged unit weight of the particle, and this F1, the force will be proportional to the submerged unit weight of the particle. So, we can write it like that. So, let us keep this as equation say 1. Then once we have got the force required to move, then we need to know that what will be the force exerted by the flowing fluid just on the surface of that particle. So, we need to know the force exerted by the fluid, and that force we are coming, as we explained in the last class also, we are talking about the drag force, because we are going by the attractive force concept. So, this is nothing but we are talking about the drag force acting on the surface of the particle, on the surface of the particle. So, here we need to go back to our understanding of fluid mechanics, what is drag force and lift force, but of course, time will not permit us to go much back, but still we can write down the expression for drag force here as, say, this force is, if we write it as F2, if we write it as F2, then we can just write in the way that it is also proportional to, we are using CD, then of course a representative area A, and then half of rho, then u square. Basically, it is the velocity square, but here our velocity we are talking about at the surface of the particle, and that we are naming as ud. So, this ud means the velocity at this level, at a height of depth d, at a height of d, which is basically nothing but the particle size. Again, what should be this d? There are also a lot of controversy, as we say that d is the average particle size. Now, this average particle size means when we talk in real situation in a river bed, if we see that particles will be of different sizes, and then if we carry out a sieve analysis of the particle, we will be finding that gradations are different, and then which value actually we will be taking. Some support that, well, we need to take D50, some say the D90, like that. Well, anyway, now after lot of analysis, it is seen that this size, though these are different, D50 and D90, but say it does not influence that much on the frictional characteristic ultimately. I mean small differences, because these difference main particle size is there, and then within that particle size when we are talking about D90 or D50, it do not make much difference, and that is why people go with D50 in most of the time. Well, now we are considering that suppose it is given that D is the value of the particle size, then we can go for UD, and UD is the velocity at a depth t. That is by concept we are writing that this is the force. Now, what will be this area? Again, when we are talking about a particle of diameter d, then area is also not known, because this will be different. If it is a flat particle, then the area will be more. If it is a round particle, it will be different. So, generally we can just consider conceptually that this area, like that volume is proportional to the diameter cube, area we can have as proportional to the d square. So, what we can write that F2, then let me write as equal to, and we are introducing another proportionality constant A2, which will take care of all the proportionality. So, this is say CD, and this A we can write now as say d square. D square means the diameter square, and then it is half rho UD square. Okay. So, this is what our expression is. Then again from here we can just express what will be the CD and what will be this UD. Here just we are writing UD, but in reality it will not be possible to know what will be the value UD directly. So, we need to simplify that, and we need to have it in a form which value we can have very easily. Well, so this value we can now modify starting from this formula. Well, so we are writing that F2 is equal to A2 into CD into d square into half of rho UD square, half of rho UD square. Okay. From that, if we see that we have already one relation that we analyze, that is what is the velocity distribution. We are interested to know what will be the UD at this level. At particles are like this, what will be the velocity UD at this level, and we can take help of our understanding of the velocity distribution, and that we had that U by U star. Already we have discussed that in our last class. This is a U by U star is a function of shear Reynolds number, that is nothing but U star d by nu. In reality it is U star y by nu, U star, okay, let me write it as U star y by nu first. Y means any depth, U star y by nu. This is the shear Reynolds number. Now, for our case here, say when U we are interested in UD, that is what is the velocity. This expression is general, at any depth y we are talking about this velocity U. Now, our interest is what is the velocity at this top when depth is d. So, we will be writing this as UD and U star, and this is a function of, that is why our depth will also be U star d by nu, U star d by nu. And then we can put that, as we said that UD we do not understand what the value is, or it is difficult to measure. So, we are bringing it in terms of U star f, then U star d by nu. Okay. So, UD is a function of Reynolds number, shear Reynolds number, and a product of U star. Well, then again if we go back to our fluid mechanics understanding, then we have that CD, that is the coefficient of discharge, sorry, this is the drag coefficient. Generally we write this capital D, let me write it as capital D, C capital D, C capital D, that is the drag coefficient CD is also a function of, we can write this is also a function of Reynolds number, that we can write U, and we are talking about drag force at this level. So, the corresponding velocity here is U d. Corresponding velocity here is ud and our depth is d. So, ud d by nu. CD is a function of ud d by nu. That means, it is a function of Reynolds number, but this Reynolds numbers we are not talking about the shear Reynolds number. We are talking about the Reynolds number at a depth d for the velocity actually ud, Reynolds number for the velocity ud, and our depth here is d. Okay. So, this is the drag. Now, this if we write ud in place of ud, if we just put u star these things, then what we can write, that CD is a function of, so ud I am replacing by u star, and that I will be writing on the right side, and this is say f of u star d by nu, that is there, and this part u star ud is replaced by u star into this, and then d by nu. So, again what we are finding finally, that CD ultimately this is also a shear Reynolds number, this is also a shear Reynolds number. So, it can be written as a function, different function, say f1 of say u star d by nu, u star d by nu. So, we can write CD as a function of say u star d by nu. Of course, these two functions are not equal functions. So, if I am writing this as f, this can be written as say different function name we can give, say f1, then we can write this as f2, which is combining this function as well as that function. Okay. So, this we can write CD is equal to that one. Now, replacing this value of CD in terms of shear Reynolds number, and then of course, replacing this u star square, what we can write, let us see. Again, let me just keep this equation here, f2, just for our convenience, we can keep this original equation here. We were writing that a2, then CD, then d square, then half of rho ud square. And now, let me replace this term, that is f2, we can write this is equal to a2 will remain as it is, and then CD we can write as a function say f2 into u star d by nu, kinematic viscosity. Well, this diameter d square will keep as it is, plus rho, and then this ud square, that we can write as u star, because ud we know that is u star into function of u star d by nu, that we have already expressed. So, when it is, this part is basically ud, so when it is square we can write u star square and this function square. So, that way we can write rho. Okay. Now, so rho is here and this part we can write like that. And then what this value of u star? We know that u star is nothing but it is equal to root over tau 0 by rho. So, here it is coming again the shear velocity, and we are talking about the shear stress at a particular point. So, this shear stress at a particular point and divided by rho, shear at a particular point means we are talking about the bed shear divided by rho. Okay. So, this we can write, this is equal to f2 equal to a2, and all these are now becoming functions of u star d. So, we will keep it as a function of u star d. So, d square I am bringing here, this is not plus, this is a product, o square d square dot. So, this is basically half, this is half is there. Okay. Then we are writing that this is a function of u star d by nu. Combining all these function we can give another name, say f3, and then we can write this one as d square is already written, u star square, that we can write rho. Now, u star square will be tau 0 by rho. So, here we are introducing the tau 0, that is the shear stress term, and this is already included there. So, finally, this expression can be written as F2 is equal to I think half was there. So, let me put this half here, half. So, half of A2 this square and tau 0, this rho is going, and then it is a function of u star d by nu. Well, so let us put this equation, let us put this equation as equation 2. Let us put this equation as equation 2, and already we have our equation 1. Already we have our equation 1. If we go to that, this is our equation 1. Now, what is that? For incipient motion condition, for incipient motion condition, we our basic condition is that these two forces are equal. So, what we will write? For incipient motion condition, F1 is equal to F2, and of course, when F1 is equal to F2, you are talking about what will be our bed shear stress tau 0. Tau 0, that we can now write as, because when these two are equal, that is what our critical condition, this is what our critical condition. So, at critical condition, this bed shear stress we are writing as tau C, say critical bed shear stress. So, equating these two, we can write it as say A1 G rho s minus rho, this is the expression for our equation for F1 d cube is equal to half of A2 d square, then tau 0 and f some function of, we are writing u star d and nu, not tau 0 now, we will writing it as tau c, we will be writing this as tau c, and f we have generalized, now it is a function of u star d by nu. Well, from here this part are constant, d cube d square is there, so 1 d will be there, we can just go as say let me keep tau c here, tau c, and then let me write it as g rho s minus rho, and then d, 1 d will be left here, and then this is equal to, we can write this is A1. So, twice A1 by A2, we are carrying that one, bringing this one here into this, we can write as 1 by function of these things, or again in a sense we can write that this is a function of well, to avoid confusion, let me write is as 1 by f u star d nu, but it does not matter 1 by these things, or we can write it as a function of this one. Okay. So, now this expression to say twice A1 by A2, and we can say that this is basically a function of u star d by nu. Well, now f dash, suppose this is a function. So, what we have seen that this critical shear stress, our interest is to know this critical shear stress, our interest is to know this critical shear stress. So, this critical shear stress divided by z and then rho s minus rho, basically it is the submerged density we are talking about, that is why it is coming like that, and the diameter of the particle d, and then some constant, this part is some constant, and then it is f dash u star d by nu, and this term was expressed as, that is, this term was expressed as tau c star. Let me write here, this term was expressed as tau c star is equal to, ultimately we can call tau c star is equal to a function of, ultimately it is again a function, this is, these are constant basically. So, as say for a given dimension of the particle, for a given dimension of the particle, this term will be more or less constant. So, we can just consider that tau c star is proportional to, or a function of, rather not proportional, is a function of u star d by nu, and this u star d by nu we can write as r. So, this can be written as function of r c star. This r c star is called Shear Reynolds number. This r c star is called Shear Reynolds number. So, this tau c star, which is related to the critical shear stress, can be expressed as a function of Shear Reynolds number R e star. Okay. Now, with this very basic relation, let me write somewhere it is in a very clear form, that is say, okay, let me take this part, tau c star is equal to a function of say r c star. Okay. This ultimately we are getting. Well, up to this much the analysis what is being carried out, of course, this we can do by dimensional analysis as well, considering that what are the factors influencing. Well, I can give a brief view of that, but now right at this moment we can consider that tau c star is equal to f r c is a function of Shear Reynolds number, and then Sealed, he did lot of experiment, lot of data were collected by his follower also, and then a graph was drawn. So, these very basic relation with the understanding from the analytical concept was used, and a lot of data were collected from experimentation, and then these were plotted by Sealed, and of course, some other experiments has also been done later. Well, how the Sealed got this relation, that you can concentrate in the slide now. On this side, if we plot r c star, that is the Shear Reynolds number, okay, and then on this side if we plot the tau c star, and what is tau c star, that we know that this is equal to tau c divided by g rho s minus rho into d. So, this is what tau c star, and Shear Reynolds number, that is r c star, is nothing but this is equal to u star d by nu. Well, these two were plotted, can be plotted, and with the scale say it is in log scale, it is 10 to the power minus 2, starting from very small value, then say here it is 10 to the power minus 1, and here it is say 1. So, that way we can go. Then on this side it is 10 to the power minus 2, then 10 to the power minus 1, then 10 to the power 0 means 1, then 10 to the power 1, 10 to the power 2, 10 to the power 3. So, that way if it is plotted, then these observations form in a scattered diagram for different values, and then it could be drawn in the form, the seal what he got initially, he was able to draw it in this form, and then it was going like this. That means, after certain value of r c star, when r c star exceeds certain value, then this part become almost straight, and we can have that this r c star, for that r c star tau c star we can have constant almost value. But these experiments were carried out with a less number of data. So, this curve we refer as Sealed curve, Sealed's curve. Then after that, Yellin and Karahan in 1979 they published some work with the same experiment, but with lot more data, and the curve could be extended up to this portion. Say their curves came like that, and then it went almost in the same direction, then it was going like this. And then that curve we can call, that is why as per their name, say Yelin and Karahan in 1979. Well, so they gave that data, and from that now we have a general relationship between this RC star and tau C star for a wide range of value, And now question is that how to find the tau C star, or our interest is to know what this value is tau C. How to find that? Basically, how we do it, or how it is to be done, that first it is a trial and error procedure is adopted. Trial and error procedure need to be adopted. Of course, some approximate method is there, but we can take trial and error procedure. Means by simplifying this relation, we can have some approximate value. Generally, a tau C star is assumed, tau C is assumed. So, once we assume the tau C, we know what is U star. U star is nothing but root over tau C by rho. U star is nothing but root over tau C. Tau C is nothing but the bed shear. So, we were getting tau 0 by rho, but it is the same thing because it is the bed shear, but in critical condition. So, we can write tau C by rho. So, that way we can get U star. We know, suppose a particular size of the bed material, the effective size we can take, then we know this new value. So, for that tau C we will be getting a RC star value. Now, from this RC star, from the graph we need to see what is your tau C star. So, once we get the tau C star, again rho, G and D are known. So, we can find out what is tau C. Now, our assumed value of this critical tractive stress tau C, if it is matching with the value that we are getting from the graph, then it is okay. That means our assumed value is correct. If not, we need to assume another value of tau C, calculate RC star, see what is the value of tau C star, and that procedure will continue. And then once we get the two value are matching, then we can have our required value of tau C. So, that way for a particular situation we can get the value of critical tractive force. Well, but for irrigation canal, say because generally when we talk about irrigation canal, then these sizes are almost known to us, that it will be say around 1 to 2 meter width, and then say it will be having a depth varying between say 1 to 1 meter or around that. So, now for those situations several experimentation has been done, and then some investigators have given the value of tau C, critical shear stress, as a direct expression relating this value, that is G rho S D. Using this expression they have given this value. So, some empirical direct relations are also there, and these are also empirical, but it is more extensively done putting lot of value, and so the tau C star calculated by this value will be more accurate. Of course, assumption is always there in all these analysis. Well, with this understanding of tau C star or this tau C shear stress value, now we can go to just see that when our value of this tau C exceed, when our value of tau C exceed, that is the not tau C, when our value of bed shear stress tau 0 exceed, then our particle of the bed starts moving. That is when tau 0 is greater than tau C, then the particle starts moving. Of course, if tau 0 exceed by small amount, what will happen? Tau 0 exceed by small amount, then the tau C, then what will happen? Then when tau 0 exceed by large amount, what is happening? Again, the small and large are very vague, as I said earlier. So, how much we should give some index? And as I said earlier, this sort of motion we can analyze by dimensional analysis also. And when the sediment part is moving into the fluid or water, suppose when the sediment is also in motion in the water, then the entire flow we deal as a two-phase motion. We deal as a two-phase motion. And this two-phase motion, when we find, then this sort of motions are affected by several parameters. And of course, in the last discussion, we have seen how Shear could relate this relation up to incipient motion condition. And then after that, when incipient motion condition is over, I mean we are exceeding this value, then what is happening? These are generally always in the observed form, and some relationship, some equations has been derived on that. That is again some semi-theoretical relationships are there, and then generally dimensional analysis become very necessity for having for understanding what sort of parameter can be related, for having that sort of equation. Well, so let us have some idea on these aspects also. So please concentrate into the slide. We will be discussing something on two-phase motion. Okay. Well, to discuss the two-phase motion, what we basically mean by two-phase motion, that definition wise we can write, that is a simultaneous motion of solid and liquid phase. By solid, actually we are meaning that the sediment part. In our hydraulics, in the flow of channel, we are meaning solid means the sediment part. Of course, the sediment can be moving along the bed, it can be moving sometimes I mean little higher into the bed or getting completely mixed up with the flow. So that things will be coming. But in any form, simultaneous motion of solid and liquid phase is termed as two-phase motion. And several parameters actually influence this sort of motion. To have a proper understanding of this two-phase motion, we need to have proper understanding of several parameters, how they are interacting. And of course, when we go for deriving some relation, the physical understanding is in one hand, but sometimes we observe something, and the physical process sometimes is so complex that we cannot really have a proper understanding of what the internal things are going on. But still, at finer level, although we sometimes may not understand, but we can at least have the understanding that some of the parameters are obviously influencing the flow. And those parameters, if we take into consideration, then we can derive some mathematical model out of that. Well, let us see that following, and that way we can just summarize that following 7 parameters are important. So I emphasize that we are using the term important. It is not that other parameters are not influencing, or other parameters can also be influencing, but which are significant, that way we are writing that following parameters are important. So the fluid density, say rho, that we are talking about. Fluid density is definitely influencing. If a high density fluid is coming, this will be its impact on erosion will be different. And then grain size density, this is obvious. If a lighter size is there, it will be eroded quickly. Of course, quickly means again there is it is not that straight way. Lighter means if it is very finer and have suppose lot of cohesive property in it, then whole phenomenon may change. But considering this as incoherent material, that means without having cohesive property, we are just talking about. So without having that cohesive property, this density less means it will be eroded quickly. Then kinematic viscosity, that we are always getting that nu is a influencing parameter. Then typical grain size, that I have already told, the typical grain size, say if we give as d, and what will be the typical, that is why typical term is used, whether it should be d 50, d 90, but we are considering this as typical, and we can say that okay, right at this moment we can consider this as d 50, say, of the particular size, or by the analysis what we are getting from the field, from that we can take say d 50. Then flow depth h is also influencing the erosion. then shear velocity u star. This is very important element. This is very important element. And the submerged weight of the grain, and then that is basically, so this grain density I am writing as gamma s. So, this is basically nothing but gamma s minus gamma into g, or say we can write as gamma s in a single term, that is the submerged density, submerged unit weight of the grain, and that of course we can write as g into say rho s minus rho. Okay. So, these are the parameter that is influencing. Basically, submerged density mean here extra term is coming g, already rho and rho s we are taking here, but this we are keeping as a separate parameter. Well, now we know the very fundamental concept of dimensional analysis, and so in this part, if we carry out dimensional analysis as these are the influencing parameter, if we take repeating variable as say rho and say depth, the typical grain size d, and if we take the u star as the repeating variable, then we can by dimensional analysis we can see that interaction of these parameters can be grouped into some non-dimensional term, and we can say that these non-dimensional terms are influencing the flow, and that is one term is very familiar to us already, that we can name as grain size Reynolds number, that is say u star d by nu. We are using that already. We are talking this as we were talking when we were doing the seal theory, then we were just talking about that particular value as shear Reynolds number. The same term, we can name this as a grain size Reynolds number, because in this Reynolds number our length characteristic that is coming. Reynolds number general expression is basically u then L then say nu, or say we can write rho v L by mu or u L by nu. This L is basically the length characteristic, and this length characteristic in this case is coming, though in fact when we were analyzing in our seal theory, it is the d is coming because we are talking about a shear force acting at the depth of d on the top of the particle size, but in general ultimately this length dimension is coming as the diameter. So, we can name this as a grain size Reynolds number x. And then another number, mobility number is coming, that is rho u star square then gamma s d. Again this term is nothing but the tau c star. This term is nothing but the tau c star. As we can see that say u star square is, say we know that u star is equal to root over tau 0 by rho. So, this is equal to tau 0 by rho, u star square is equal to tau 0 by rho, and gamma s already I have written that gamma s we can write as here itself I have written gamma s we can write g rho s minus rho. Okay. So, this term is nothing but we can write it as, say it is tau 0, rho and rho will get cancelled, this is g rho s minus rho into d, and that is what we got as tau c star. So, by dimensional analysis also we are getting that these are the terms which are basically related, which are basically influencing the flow phenomenon when it is in two-phase motion. Then of course, the depth factor z that is also used, this is say h by d, and then this grain density w, this is another dimensionless term, that is rho s by rho, these are also influencing the flow. But out of these we can see that this can be related to that one, this can be related to that one, that is for critical stage of mobile bed. Now, we have seen that when we are talking about this dimensionless parameter, two-phase motion is influenced by all these parameter, and when it is in critical stage of motion, that is when just in the incipient motion condition, then this x can be related to y in critical condition. So, we can write that for critical stage of a mobile bed, y critical is a function of x critical, y critical is a function of x critical, and that already we have got in our earlier discussion, that tau c star, which is basically we are talking about tau c star in critical condition, and this y critical what we are writing here is nothing but the tau c star. So, we are already getting that tau c star is equal to a function of say r c star, that we got, and this x CR is the nothing but this r c star. So, same expression basically. Well, and then this YCR mobility number. Now, this number is stated as mobility number, and how much amount will be eroded, or what will be the stage of erosion or say stage of scouring, that can be studied in terms of a number that we call that ratio of mobility number, because mobility number is very important, which is influencing the this sort of motion or movement of particle from the bed. And without going much detail, we can write the ratio of mobility number, say eta is equal to y by y critical. That means, at a particular instant of time, I mean for a particular velocity and particular combination of all these parameter tau c star what we are getting for a particular combination, if we calculate this mobility number, and we know that what is the mobility number in critical condition, which is a function of say x critical, that is the r c star. So, we can find a ratio eta, and it is seen that when eta is less than 1, when eta is less than 1, then basically we have not reached the incipient motion condition. There is no flow will be moving, no flow will be moving. Well, here we can have a diagram like that, say this is the bed, and there can be some roughness of course, and then we can see that we can draw a line. This is we can call epsilon, means up to certain depth. Why we are dividing? Because in some of our later period we will be experiencing those things. Say on this side we are drawing the y depth. Okay. Now, when eta is less than 1, mobility ratio of mobility number eta is less than 1, then our particles are not moving. So, we are getting a plane bed, without sediment movement, and for that situation our all understanding of rigid boundary channel are valid, because our particles are not moving, it is just behaving like a rigid boundary. But when our eta is greater than 1, then particles start moving. Initially, it will be just leaving from the boundary, and it will be spreading like this in the bed only, it is spreading, and gradually it is moving. So, it is just spreading in the bed and it is moving. So, that is the incipient motion condition we are getting. Then when eta gradually exceed that value with the increase of discharge, then the stress increases, and then our eta exceed that value. Then when eta between 1 to 10, particle, if I consider it start jumping like this, it will follow some path like this. Say we can call that particle part of the material, material of the bed, I am putting bed. So, it is jumping, then rolling, like that particles are moving within a very small distance epsilon. That is why this distance was shown, within a small distance epsilon from the bed. And that part of sediment movement we call as bed load, Okay. Generally, this term will be coming in our many analysis, that how much is the bed load, how much is the suspended load, like that. And then when eta exceed further, Suppose eta is exceeding beyond 10, then the particle will start moving into this portion in a very zigzag way with lot of turbulence, and this will be the part of suspension. We do not know exactly which part it will be. So, it is moving like that, and then this part is actually we refer as suspended load, suspended load. So, in two-phase motion we get some particle moving just near the bed by jumping, rolling, and then this sort of motion or this sort of sediment component we call as bed load. And then some other particle are moving into with the increase of shear stress, with the increase of force, it is moving, it is getting into the main flow, and then it is getting completely mixed up with the flow, and then this flow we call as a suspended load. So, these two components we will be getting in two-phase motion. Well, with this very basic understanding of the suspended load and bed load, now we can talk about regime of flow. We can now talk about regime of flow. So, what we mean by regime of flow, that is for shear stress greater than critical shear stress, greater than critical shear stress, the particles from bed start moving and the bed and the flow surface takes different forms, and that is, this is important, that the bed and the flow surface takes different forms and can be classified under different regime of flow, different regimes of flow. So, when bed form is changing, then actually the surface of water is also changing. Okay. So, first of course, as we know that it is this plain bed without with no sediment motion, this is just as rigid. Then when it start moving, it forms ripples on the bed of the river. Maybe many of us we are traveling in the river, and if we find that some sand deposition is there in the river, we will be finding that some undulations, some small undulations in the bed, and that sort of undulation we call as ripple. And then when it is this undulation gradually increase in size, and then that is called as a dune, that is a different name, dune. Now, of course, this we will be discussing just in a qualitative way, means how much can be the size, it is not that definite, it is not that definite. In laboratory level it will be very small, in the field level sometimes it will be very small, but for a bigger river this sort of dune and ripples can be of very large dimensions as well. So, this just we will be talking in qualitative way, not exactly the amount, how much size it can be. And then we talk about transition, that means between ripple and after ripple and dune there will be transition, and then in transition basically there are few stages. Say initially what the ripple, okay, let me draw a figure that will be better. Say this is a bed, and then initially the bed will take a form, well, bed will take a form like this, and that is very most of the time we see, and this, but the surface is not that much disturbed. Well, that is what we call as a ripple, and then gradually these sizes are increasing, gradually these sizes are increasing, and then we are having some undulation there, and this is called dune. So, this is dune and this is ripple. Of course, many find that it is very difficult to distinguish between these, while these sizes can go up to say 0.4 to 0.3 meter say maximum, and this can be it can go say 0.4 meter, 0.5 meter in smaller size, but in bigger size it can go up to higher, larger dimension also. And because the flow is moving here, the difference is that when it is forming a dune, then the flow coming here is getting moving like this, and there is a separation of flow, and here there will be separation of flow, means there will be some deformation, and this will induce some amount of energy loss in this part. And because of this movement, say flow is moving like this, and here also the flow is moving like this, and then it will be coming down, because that will be a low pressure zone, and then flow will be just coming down like that. Some turbulence will be created, and this is again just inducing some erosion in this part and that part. That way, in dune, this the crest of the dune is always moving in the forward direction, Sediment is of course moving in the forward direction, but the crest of the dune also in a very slow speed. Again, I do not want to quantify. That means, suppose today it is there, after several days it may be moving a few meter or few centimeter in the downstream direction. So, with a very slow speed it is moving in the downstream direction. Then after that, a time will come when the velocity is increasing, the charge is increasing beyond certain limit, then we talk about transition, means initially the dunes will be washed away, So, that is what we were talking about, this part, that transition, say washed away dune. Then after that, these are completely plane bed form, this is completely plane bed form. But the difference is that when we were talking about the first stage, say plane bed without sediment motion, here we will be having a plane bed, but there will be sediment motion. So, there will be sediment moving, and that is the difference. And one important point is that in plane bed, though it is also a plane bed, and when our tau c is critical shear stress, our bed shear stress is less than critical shear stress, no sediment motion, then also we are getting a plane bed, but the resistance, that is we were discussing resistance parameter earlier, this resistance to the flow, resistance offered by this sort of flow will be much higher, almost double than that sort of flow when there is no sediment motion. So, that is how understanding these things are very important. And then we get some standing wave like this, this is some standing wave like this, we get some standing wave like this, that is called standing wave. Okay. So, these are just in transition stage. And one more important point, this sort of flow, that is the ripple and dune, generally means it is occur in the subcritical flow condition, very subcritical flow condition, that is Froude number will be very less here. And this transition take place, this sort of things when say gradually it is increasing, Froude number is gradually increasing, and it is say Froude number is becoming nearly equal to say 1. Of course, it will not be exceeding 1, but nearly equal to 1. Then after this situation, the flow will be just another stage that is called anti-dune. It will be very big size dune, and it is symmetrical. This was just forward direction, leaning in the forward direction. This will be symmetrical like this. It will be symmetrical like this, and of larger size. And those sediments are moving, and here the surface can also be break like that. Surface can also have some discontinuity in it. Well, now the one difference is there, when this crest, in case of ripple, this crest is moving in the forward direction, but in case of dune, although this sediment is moving in the forward direction, but this crest is moving with a very slow speed in the reverse direction. So, that is why the name is called anti-dune. It is called anti-dune, where the surface can also break. Well, like that we can have different sort of different sort of flow regime, as you could see that all these different kind of flow regime we can have. Now, if you concentrate in the slide, we can discuss something on the resistance in a undulating bed, some of the critical issue we need to discuss. Well, already we have discussed that in what sort of flow, what sort of condition we can have, and then so that means when the ripple and these things forms in the subcritical zone, that already we have discussed. Then we did discuss that in supercritical flow only we can have the anti-dune, and this we can have ripple and dune, okay. And then resistance to the flow is higher when it is a plane bed with sediment motion, that also we have summarized, that is almost double. Resistance is almost double, is equal to resistance with sediment motion, is almost double that of the resistance without sediment motion, okay, without sediment. So, that is also one important aspect. Then another aspect that we need to know, that when sediments are moving and suppose these bed forms are occurring like this, then here when the flow is occurring like that, the resistance offered is not only due to the roughness of the bed, but also due to the energy that is lost or the resistance offered by this sort of undulation. As we can see that here, suppose it is coming with a velocity v, in this portion the velocity will gradually drop to v2. If it is v1, this will be v2. If the discharge q is same, then it is dropping. Then it is a case of say suddenly velocity is dropping, and then we can find that how the velocity, due to expansion of that velocity, how the energy get lost. And that is why this loss of energy means some energy get consumed in overcoming this sort of situation. Some eddy will be forming like that, and so considering all these losses, ultimately our entire resistance to the flow phenomenon will be different from the resistance of the plane form without sediment, or we can say that resistance to the rigid boundary channel. And that is the very basic need of discussing all these cases that we have discussed, that flow in a mobile boundary channel means uniform flow in a mobile boundary channel, because we are talking about resistance flow formula, and resistance behave in a different way in mobile boundary channel. And of course, when we will be going for practical work, we need to have understanding of this phenomenon, and when we are using the resistance parameter, then we will have to consider all these different factors in it, and then only we will be able to come out with a proper calculation and proper design of various river structure, various irrigation structure. So, with that we are concluding today's discussion. Thank you very much.